Ivan?
We see you, we hear you, everything fine. We see this nice Университет МГУ по инженерии in Russian.
Oh, okay. Okay, thank you, Ivan, for your emotional remark. So, good morning, friend in Russia. Good afternoon, friend in China. We are in two time zones. You are the morning of Russia, and we are the afternoon of China. The internet magically connects us in this seminar space, allowing us to communicate with each other face to face. I will introduce myself. My name is Jia Yunde, a professor of computer science at Shenzhen MSU BIT University, and a professor of computer science at the Beijing Institute of Technology. And I serve as the director of the Provincial Lab of Machine Perception and Computing. It's my great honor to co-chair this seminar with Professor Ivan Osledis and enjoy the presentations of the 12 outstanding scholars with you. Let me briefly introduce the background of this seminar. Shenzhen SMU BIT University is a non-profit Chinese foreign cooperative university jointly funded by the Moscow State University, Russia, and the Beijing Institute of Technology, China, in 5 years ago. We know that SchoolTech is 11 years old, but SMBU is only 5 years old. We are still childhood, a little baby. So in our university, nearly half of the faculty and staff are from Russia. Not long ago, our university strongly encouraged us to carry out academic exchanges and cooperation with scientists in Russia. Our research interests are computer vision, pattern recognition, optimized computing, machine learning, and other hot topics in the field of AI. In recent years, we have published hundreds of papers in top AI conferences and journals. And we have also read the papers published by SchoolTech scholars in top conferences in this field. Your achievements in this field are outstanding and first attracted our attention. Therefore, I emailed Professor Ivan, and he's very glad. He gladly agreed to co-chair the seminar and suggested that it be held today. Here, I'd like to thank Professor Ivan for his enthusiasm and support. I would also like to thank Professor Wu Xinxiao, Miss Anastasia, and Mr. Shun Ruoben for their elaborate organization, service, and hard work. Finally, I wish our seminar success and a wonderful day to our friends. Thank you. Next, we invite Professor Wu Xinxiao to be brief us on the organization of the session. Xinxiao.
Okay, thank you, Professor Jia and Professor Ivan. Let me briefly introduce our seminar. And today we have 4 sessions. And in each session, 3 speakers are invited to give their talks. And we also invite 4 professors from SchoolTech, SMBU, and BIT to be session chairs. Professor Mingtao Pei from SMBU and BIT will host session 1. And Dr. Alexander Mikhailov, the senior research scientist from SchoolTech, will host session 2. And Professor Xin Xiaowu, it's me, from SMBU and BIT will host session 3, and Professor Dimitri Dailov from ScoreTech will host session 4. Okay, next, please join me welcome Professor Pei-Ming Tao to host session 1.
Okay, thanks, Professor Wu. Good morning and good afternoon, ladies and gentlemen. This is Ming Tao Pei from SMBU and BIT. Welcome to the first session of this seminar. In this session, we invite 3 outstanding speakers from BIT and ScoreTech to share their research with us. The first speaker is Zhi Gao. Zhi Gao is a 50th-year PhD student of the Beijing Laboratory of Intelligent Information Technology, Beijing Institute of Technology. His research interests include pattern recognition, machine learning, computer vision, and Riemannian geometry. He has published papers in TPAME, TNNLS, pattern recognition, 3PR, ICCV, NeurIPS, and AAAI. Now, let us welcome Zhi Gao to give us the presentation about hyperbolic feature augmentation via distribution estimation and infinite sampling on manifolds. Zhi Gao, please.
Okay, thank you, Professor Pei. Let me share the screen. Hi, Professor Pei, can you see my slides?
Yes.
Is it
Yeah,
okay?
we can.
Okay, thank you. Hello, everyone. This is Zhi Gao. I'm a PhD student at the Beijing Institute of Technology. Today, I'm very glad here to share our recent work with you. The hyperbolic feature augmentation via distribution estimation and infinite sampling on manifolds. This work has been accepted by NeurIPS 2022. Here, I would like to thank my advisors and co-authors, Professor Yuwei Wu, Professor Yunde Jia, and Professor Meritash Harandi. The background of this work is many recent work reveals that much real-world data, such as the images, the videos, the graph, and the neural language, has a hierarchical structure. For example, the animal images have the hierarchical structure according to their species information, and there are 2 hierarchical structures in the ImageNet datasets. In addition, graph data has more obviously hierarchical structure. For example, some rows in the e-commerce platform system can be constituted as a tree. The hierarchical structure is consistent with their semantic labels. So, utilizing and preserving the hierarchical structure benefits to the model. Okay. The next question is how to preserve the hierarchical structure. The hierarchical structure, it is a non-Euclidean structure, and the Euclidean space cannot model it well. In contrast, the hyperbolic space can well capture such hierarchical structure. The hyperbolic space is a smooth Riemannian manifold, and it is characterized by constant negative culture. It has the hyperbolic space. It has an important property. Its space volume grows exponentially with the radius. All we can see is the distance in the hyperbolic space is different from the Euclidean distance. For example, this is a hyperbolic space, and there are 2 points in the space. Their Euclidean distance is 0.36, but in the hyperbolic space, their distance grows away from the origin. Thus, the shortest path is a curve towards the origin instead of a line. In this case, this property is very suitable for the hierarchical structure. It can model the data as many leaves as possible. So, based on the property of the hyperbolic space, there have been much work about learning algorithm in the hyperbolic space. There is a common used framework in the hyperbolic space. The input could be the original data such as the images, videos, graphs, and language. Note that this work of Kurutov et al. Is a pioneer work. It is the first work to introduce the hyperbolic space to computer vision. It opens a new direction for Riemannian learning algorithms. Then, based on the input, a feature extractor is used, and following a exponential mapping to obtain the vector in the hyperbolic space. Finally, a prediction model is used for classification, for detection, or for regression. And these methods have achieved state-of-the-art performance. Despite their success, there are still some challenge for learning algorithms in the hyperbolic space. The one is existing algorithms usually face the problem of insufficient data. Similar to learning algorithms in Euclidean space, collecting and labeling data is expensive. For example, as mentioned above, the animal images have the hierarchical structure. However, labeling the fine-grained labels requires much expert knowledge, and collecting the data of rare species is difficult. In this case, using the small amount of data will cause the overfitting problem. So in this work, we focus on this issue, and we want to solve the overfitting problem in the hyperbolic space. Here, we propose a hyperbolic feature augmentation method. We want to generate diverse and discriminative hyperbolic features, solve the overfitting problem. And our method has two parts. The first one is we introduce a meta-neural ODE distribution estimation scheme to estimate the hyperbolic feature distribution. Then we derive an upper bound of the augmentation loss. This enables us to train a hyperbolic classifier using infinite augmentation. Here we choose to perform augmentation in the feature space instead of the original space, because the augmentation in the feature space can save much resource consumption. This is the framework of our method. Similar to existing methods, we use a backbone to extract hyperbolic features. Then we employ a hyperbolic normal distribution to model features. We meta-learn a neural ODE module to estimate the feature distribution for each class. For example, the covariance matrix, the mean, and the culture. Then we sample infinite features from the distributions to train the classifier. This is the used hyperbolic normal distribution, the raft distribution. It has 4 parameters: the culture, the mean, the covariance matrix, and the prototype. For a sampling process in the hyperbolic space, there are 4 steps. It can be summarized that the hyperbolic space is a Riemannian manifold, and we first sample a vector v hat in the tangent space at the origin. Then we transform this vector to the tangent space at the prototype P. Finally, we map this vector to the manifold and we obtain the sampling vector Z. The motivation of using neural ODE to estimate the distribution is we want to avoid the estimation bias of insufficient data. Here we donate the distribution parameters as chassis. It can be culture C, the mean, mu, or the covariance matrix sigma. The estimation process is formulated as
Recording in progress.
term. After obtaining the distribution, we sample features to train the classifier. Here we use a distance-based classifier, and we sample infinite features to train the classifier W. The sampled features are donated by Z. The loss function is this one, but it is difficult to compute because there is a mathematical expectation, and we cannot directly compute the mathematical expectation. So we here derive an upper bound of the loss function. In this case, we minimize the upper bound to train the classifier W, not the original loss function. It makes the learning process with infinite samples feasible. There are the experiments. We first evaluate our method on the few-shot learning tasks, and we compare our method with existing Euclidean argumentation method and some few-shot learning method. Please note that in the table 2, there are also some hyperbolic methods, the culture adaptive meta-learning and the hyperbolic prototype. There are two few-shot learning methods in the hyperbolic space. We can observe that our method has better performance than compared Euclidean methods. This confirms that such practical datasets, such as the mini ImageNet, the CUB, and the CFAR, has the hierarchical structure. In addition, the comparison with the two hyperbolic algorithms and our ablation study shows our argumentation is indeed useful. Then we evaluate our method in the continuous learning task. Continuous learning method usually use a small amount of memory to store all the data. But if we use such inefficient old data to train the model, it will cause the overfitting problem. So here we perform the argumentation for the old data, and the results are shown in the two figures. Our results are donated by the red line. We can find that our method has better performance than the compared methods. Some of them are argumentation-based methods, and compared with a hyperbolic algorithm without the augmentation, the green line, our method still has some improvements. This shows again our augmentation, our feature augmentation is useful. Then we evaluate the neural ODE module. It is in our method, the neural ODE module is used to estimate the distribution. So here we compare it with directly computing. For example, we directly compute the mean of some field-driven data. In this case, only 5 samples are given for each class. So in this case, we can find that the neural ODE module has obviously less MSE error than directly computing. I think the reason is the neural ODE module, it learns some prior knowledge to estimate the distribution. These are visualization results. In the left figure, we visualize the feature distribution, and our augmentation makes a more robust classifier. For example, we can see the blue class. Here, the blue star is a training data. It is biased to the test data. The test data is the blue square. In this case, the original classification boundary is the yellow dashed line, this line. After the augmentation, the augmented features are these blue dots, and the classification boundary is the black line. In this case, the test samples are correctly classified. In the right figure, we visualize the images corresponding to the augmented features. We use an off-the-shelf GAN model to generate these features corresponding to our augmented features. We can see that our augmentation features are diverse. Okay, in summary, the first one is hyperbolic. Our hyperbolic feature augmentation can well solve the overfitting problem in the hyperbolic space. It has less resource consumption and brings much intra-class variance. Then we can use a neural ODE module to estimate the distribution if few samples are given. Third is the derived upper bound provides a feasible way for Riemannian algorithms. If in some case, if the loss function is difficult or high cost to compute, we can derive an upper bound of the loss function to solve this issue. That's all. Thank you. Our code comes soon, and this is the code link. Thank you.
Okay, thank you for the presentation. As our time is quite limited, we may have 1 or 2 quick questions. So, any questions?
Okay. So for the backbone for your future learning, you considered ResNet and what? And CNN or only ResNet? Oh, ResNet and VG.
Sorry.
Yeah. So for the backbone of the model, you use ResNet and VGG, right?
In our experiments, we use the ResNet, not the VGG. For this comparison. Yeah.
Okay.
And, yes.
Yeah, we had a paper this year where we used not for few shot, but for metric learning, we used transformers, and we showed that hyperbolic and transformers as backbones work very well. Maybe you can look into transformers as a backbone and get even more improvement.
The work of hyperbolic within transformer, the 3PR2022 work.
Yeah.
Oh, it's a nice work. I agree with you that if we can use a transformer as a backbone, the performance, we can improve the performance a lot.
Okay, good. But otherwise, yeah, that's a very okay. Otherwise, it's a very nice work. Yeah, so it's interesting idea of and how you select the radius of the ball of in the hyperbolic space. C parameter.
In this work, we set the culture as -1, and the culture is learnable. It is updated in the learning process.
Okay, okay. So you train. It's a trainable parameter. Okay, good.
Yes.
Thank you.
Okay.
Thank you.
As our time is quite limited, thanks for the question and thank Gaozhi for the presentation again. Our second speaker is Zan Wang. Zan Wang is a second-year PhD candidate in the School of Computer Science, Beijing Institute of Technology. Currently, he is focused on the research of human-scene interaction, goal-oriented motion generation, and 3D representation learning. Now, let's welcome Zan Wang to give us the presentation about humanized language-conditioned human motion generation in 3D scenes. Zan Wang, please.
Okay. Can you see my screen?
Yeah, but only the desktop. Yeah.
Okay.
Okay.
Hello, everyone. I'm Zhan Wang, a 2-year PhD candidate from Beijing Institute of Technology. Today, I'm going to share our new paper, Humanists, Language Conditioned Human Motion Generation in 3D Scenes. This is the first work about language conditioned motion generation in 3D scenes. And this paper is accepted by Neuronics in this year. In this work, we propose a large-scale and semantic-rich synthetic human-scene interaction dataset called Humanists. Based on Humanists, we introduce a new generation task, language-conditioned human motion generation in 3D scenes. Now, imagine instructing a virtual agent to walk to the refrigerator in the given 3D scene. The agent first needs to comprehend the meaning of the instruction, including the action type and the interacting target object. Then the agent needs to be aware of the surrounding environment to generate desired interactions in the 3D scene. The right figure is a possible example, which is semantically consistent with the given language instruction in the given 3D scene. So, given a 3D scene and a language instruction, our goal is to generate scene-aware and goal-oriented human motions. However, the limitations in existing HSI datasets make it still challenging to achieve such a goal. First, they have a limited data scale, motion quality, and scene variety. For example, the left figure is an example from PROX dataset. It only contains jittering human motions in 12 indoor scenes. The right figure is the synthetic dataset, GTAIM. It only has 49 scenes and lacks 3D human shapes and diverse movement styles. Furthermore, existing HSI datasets lack semantic annotations of the 3D scenes and human motions. These limitations make it infeasible for existing methods to learn instruction-aware 3D human motions. To tackle the issues, we propose a large-scale and semantic-rich synthetic HSI dataset, Humanists, by aligning captured human motion sequence with the scanned indoor scenes. Specifically for an action specific motion sequence, we first specify an interacting target object in the 3D scene. Then we sample the valid translation and rotation parameters by employing collision and contact constraints so that the interaction between the human and the scene are physically possible and visually natural. Finally, we transform the given motion sequence without changing the local pose. We also automatically target class, spatial relation, and anchor class. For example, sit on the armchair near the desk. The spatial relation and anchor are optional for unambiguously referring to the target object. In total, Humanist contains about 19.6K high-quality motion sequence in 643 indoor scenes. Here we show some examples from Humanist, including 4 actions: walk, sit, stand up, and lie down. Each motion segment has rich semantics about the action type and the corresponding interacting objects specified by the language description. We also render some motions into videos for better visualization. Here are some render motions of the 4 actions. Based on Humanist, we introduced a new generation task, language conditioned human motion generation in 3D scenes. The input is the 3D scene and a language description for the motions. The output is the realistic human motion sequence that is semantically consistent with the language description and physically possible in the scene. So the proposed task is more challenging than previous motion generation tasks in the following aspects. First, the motion generation is conditioned on the multimodal information, including both the 3D scene and the language description. Second, the generated human motions should perform the correct action and be precisely grounded near the target location according to the language descriptions. Third, the generated human motions should be realistic and physically possible within the 3D scenes. Based on conditional variational autoencoder framework, we present a novel generative model to generate human motions conditioned on the given scene and language description. The generative model mainly contains 3 parts: condition module, motion encoder, and motion decoder. In the condition module, we employ a pre-trained BERT and a point transformer to process the input language description and 3D scene respectively. We then fuse the scene feature and language feature with the self-attention module. The scene and language features are concatenate and mapped to a joint conditional latent embedding. Notably, the learning of conditional latent embedding is crucial to our generative model as it represents compound information of the action, the interacting object, and the 3D scene context from 2 different modalities. We thus introduced 2 auxiliary tasks for classifying the action type and locating the interacting target object. For the motion encoder, we use a bidirectional GRU to obtain a sequence level feature of the input motion. Next, we predict the Gaussian distribution parameters from the concatenation of the sequence level feature and the conditional latent embedding. We then sample a latent vector from the predict distribution using the reparameterization trick. For the motion decoder, we use the transformer to generate the human motion sequence of a given duration t. We use t sin pseudo positional embedding to query the concatenation of the sample latent z and the conditional embedding. Finally, we map the output of the transformer decoder into body meshes with the simple X model. We quantitatively compare our models with some ability models on reconstruction and generation metrics, including human perceptual study. The performance advantage of our model, especially on the generation metrics, validates our model designs and the importance of the purpose of auxiliary tasks to the generative model. We also provide some qualitative generation results for each scenario. We present 3 different generation results. The first column is for reference purpose. The results show that our model can generate human motions that are diverse and semantically consistent with the language description. We further present the qualitative comparison between our full model and the ability model without auxiliary loss terms. Without auxiliary loss, the model struggles to generate the action specified by the description or locate the interacting object. Instead, our full model generates motions semantically consistent with the language description. Based on transformer decoder, our generative model can also generate motions with different durations. Here are some generated results of different durations. Under same condition and random state, the language description is in first example is walk to the end table that is farthest from the door. The second is sit on the coffee table. The results show that our model is capable of generating motions with various duration. We further demonstrate the quality of humanity by another existing downstream task, human motion synthesis in 3D scenes. Given the 3D scene and the start and end pose, this task aims to predict the human pose in between. The model pre-trained on humanities outperforms the original model trained only on props on all the evaluation metrics by a large margin. It shows that our dataset can alleviate the limitations of existing HSI datasets and potentially support more application in HSI-related topics. In summary, we propose a large-scale and semantic-rich synthetic HSI dataset named Humanis. Humanis contains human motions aligned with 3D scenes and corresponding language descriptions. We introduce a new generation task of language conditioned human motion generation. It requires a holistic and joint understanding of 3D scenes, human motions, and natural language. We develop a generative model that can produce diverse and semantically consistent human motions given the 3D scene and language description. We believe our proposed dataset and model can facilitate the HSI research. Thanks for your listening. For more details, please visit our project page. Thanks.
Okay, thanks Zhanwang for the presentation. So any questions? Well, I have a question. So are the motions in the data set appropriate to the environment? I mean, simply applying the same motion to different environments may result in unreasonable actions. Will this happen?
Yes, but our synthesis pipeline pinpoint two critical factors and physics possibility. They are also the focus and the metrics of previous works on human motion generation. So we argue that the motion satisfying these two factors are reasonable and appropriate interaction in 3D scenes. For example, in reality, human pose for sitting on the armchair and sitting on toilet may be very different. But in our dataset, if the pose satisfying the pre-trained constraints, we will treat them as reasonable results. By the way, In our supplementary way, our human study also demonstrate humanist has higher quality in terms of collision smoothness and is more appropriate compared to previous HSI datasets.
Okay, thanks.
Okay,
So any other questions?
I have a question. So my very interesting work actually on the data set. So my question is, what will happen if you give instructions that cannot be fulfilled? I don't know, sit under the bed or something like that. So how it will, what it will do?
Okay, if you give the description, sit on the bed, the human will stand on the bed and then sit, not lie down, or it just stand on the floor and sit on the bed.
Okay. Okay, thanks Wang again for the presentation. The last speaker of this session is Nikita Kotelevsky from Caltech. Sorry. Nikita.
Yeah.
Nikita is a data scientist and a second-year PhD student at the School of Institute of Science and Technology. He is currently working on Bayes methods and uncertainty estimation. He published several papers related to a combination of bidirectional inference and Markov chain Monte Carlo methods. And one of his papers was published at ICML 2022. Nikita to give us a presentation about non-parametric uncertainty quantification for single deterministic neural network. Please.
Hello, dear colleagues. First, let me know if you see me, hear me, and see my screen.
Yeah, okay.
Okay, awesome. Thank you for the introduction. Hello, dear colleagues. My name is Nikita Kotelevsky, and today I'll present the paper we recently published with my colleagues on NeoRIPS 2022. The paper is called Non-Parametric Uncertainty Quantification for Single Deterministic Neural Network. Modern applications of machine learning require not only predictions themselves, but some complementing value, which depicts how certain or how uncertain the model is in its prediction. For example, let's take a look at the picture you see on the right. And here we are classifying cats and dogs. So you see that on the first picture, there is a cat. The true label is 1, so it's a cat. And the probability our model returns for this object is pretty high, so it's correct. The opposite situation is for the second picture. We see a dog, true label is 0, and the probability is low. But when we see something which is pretty different from our training domain, our model can be still be very certain in its prediction, but we cannot even assign a true label for this because it's apparently out of distribution data. So we have to have a way or we have to have some additional value to see this, that the model is in this situation. And what are the use cases of uncertainty? Well, there is a variety of methods with possibility of rejection to predict, like misclassification detection, out of distribution detection, and adversarial example detection. It is also could be used in active learning, in acquisition functions, and in Bayesian optimization. First, let me tell you about different types of uncertainty. Imagine that we are still distinguishing between cats and dogs. And let us precisely look at the region where classes overlap. So what is going on here? This region where our model and our data is pretty confusing. And the uncertainty which is associated with this confusion, like label noise or class overlap, it is called aleatoric uncertainty. And in principle, you cannot reduce this type of uncertainty if you provide more data from the region. In the contrast, another type of uncertainty, namely epistemic uncertainty, is associated with our ignorance of data. So if you see some unusual dog or unusual cat, you can be still not very confident in your prediction. You should be, the uncertainty should be high. But in principle, if you provide more data from these regions, you can decrease the uncertainty. You cannot reduce aleatoric uncertainty, but you can reduce epistemic uncertainty. It is essential to separate these types of uncertainty because the total uncertainty could be high for both regions, where either epistemic or aleatoric uncertainty is high. But for example, for OOD detection, a special application of uncertainty, we are not interested in aleatoric uncertainty because it is known unknown. So we know that there is a region where classes overlap or there is a label noise. Thus, we have to have an access to epistemic uncertainty, or in other words, unknown unknown, to find these OOD samples effectively. In this paper, we provide a new uncertainty quantification method. And the key features of our approach and what distinguishes our approach from the competitors is the following. So first of all, our method is a post-processing method. What does it mean? It means that it could be applied to any pre-trained neural network, in principle to any. In paper, we discuss some specific type of neural network for which our method will be like more suitable, but in principle, any pre-trained neural network could be used. Our method works in embedding space of a neural network. So this allows us to reduce the dimensionality of objects we are operating with. So you know that the image domain, for example, is quite high dimensional, and embedding space compared to this initial space is more less dimensional. Our method, what is way more important, allows us to explicitly disentangle aleatoric and epistemic uncertainties. So we can use our epistemic uncertainty for example, for OOD detection and other applications I have mentioned. And our method is fast and scalable. For example, if we compare our method to ensembles, where you have to run your input data through all the members of the ensembles, here we do not need it. We can run our model, the base model, which has the pre-trained model only one, and then apply our method, and we have the uncertainty. So it is pretty fast. And let us derive our method step by step. For simplicity, let us consider binary classification problem. We consider some pairs of objects X and Y, which come from the joint distribution P. And when we solve some classification problem, we typically aim to find some rule, which is denoted here by G hat, which minimizes risk or the probability of making a mistake. So the global optimal rule is denoted here by G star. And what we are doing, we are trying to find G hat, which approximates G star. We also assume that this global optimal rule is given by a bias optimal classifier with respect to some density eta, which is also typically unknown to us. And eta is nothing but the conditional probability of y equals 1 given some input object x. Next, let us make, it's correct. Let us make the assumption that all the difference between the joint distribution on the training data set and on the test data set, the joint distribution of x's and y's, lies in covariate distribution. So if we decompose the joint into the product of marginal and conditional, we assume that all the difference is in the covariate distribution, while the conditional label distribution is the same. Next, assume that for now assume that we somehow received this approximation G hat based on our training data set D. Let us define a point-wise risk as follows. So this is nothing but the probability of making a mistake for a fixed G hat and fixed corresponding data set D, but in a given input object X. And based on the assumption above that all the difference between test and train data distribution lies in covariate distribution, we can conclude that the point-wise risk will be the same on train and test data sets. And this is important because it effectively allows us to derive some rule based solely on the training data set and then reuse it on the test and hope that everything will be all right, because, well, in principle, it should be, the point-wise risk should be the same. Let's move forward and discuss the next thing. So total risk, it admits the following decomposition. So if we add and subtract the same value, which is denoted here by R star, or the probability of optimal classifier makes a mistake, we can receive this decomposition. And actually, each term in this decomposition has some sense. So the first term, which we call here bias risk, well, that's by definition bias risk. It is associated with aleatory uncertainty because it does not depend on our training data at all. So it is just something related to the data itself. And the second term is the difference between our approximated, the risk associated with our approximated rule and the global one. It is nothing but the difference between these two quantities, and it is called the excess risk. And we will associate this term with epistemic uncertainty because, well, apparently it relies on the data we have derived our rule G hat. Let us assume that our approximated rule G hat also an optimal bias classifier with respect to another density eta hat, which is also the conditional probability of y equals 1 given x, and which approximates the unknown optimal eta x. There is the general result, regardless the form of how we approximate eta hat, we can upper bound the excess risk by the following quantity. So the upper bound is 2 multiplied by the absolute difference between these two densities. And it allows us to upper bound the total point-wise risk using this quantity. And for the binary case, we know the closed form expression for bias risk. It is just the minimum between these two variables. So far, we haven't discussed how we will choose G hat or eta hat from which we can derive G hat. But now this is the moment. So we will use a specific form of Nadaraya-Vatsa kernel regression. Why? Because it has some useful asymptotical properties. Namely, so yeah, let us first discuss the approximation. So in multi-class case, when in fact there are C classes, the form will be the following. But if you substitute C by 1, we will just have eta hat. So the approximation looks like this, where KH is some multidimensional kernel with bandwidth H. And if we choose as our approximation this, we will have the following property. The difference between eta hat and eta converges in distribution when the sample size increases to the normal. And this normal has 0 mean and this variance. And fortunately, we can estimate each quantity in this variance using only our training data set. We will discuss it later. So, okay, we know that the difference converges in distribution. And what can we do next? Next, the L, as you remember, it is just the upper bound we had for risk. Now we want to, we still have the randomness here because of our data set. And if we take the expectation over all possible data sets, we can receive the following measure of total uncertainty. So this term is exactly this, but for general case when there are many classes. So if C equals 1, it's the same. And these terms appears here because of the following fact. So we know that this random variable is normal, but here we have expectation of the absolute value of this random variable. And we know that expectation of this absolute normal equals to this. That's why we have tau here. Tau squared is the variance of this normal. So yeah, that's what I write here. And that's why we have just the standard deviation. And actually we can estimate each term within this tau using only our training data set. What we have finally, we have the total uncertainty, which consists of 2 terms, and each term has a meaningful sense. So the first is the aleatoric uncertainty, and the second is epistemic uncertainty. Yeah. So let us move to the experimental results. I'll present only part of the experiments we did in the paper, namely on OOD detection. What we have here, the table on the top, we were trying to distinguish in distribution samples from Cypher 100, from out of distribution samples, from CVHN dataset, LSUN, and another artificial dataset. We computed our epistemic uncertainty estimate for each of these samples, and then, well, because we know what comes from in distribution and from out of distribution, we could compute ROC-AUC score, and this is the values you see here is exactly ROC-AUC, and we can like reason how well our method detects out of distribution samples. And you see that our method, namely nuke, outperforms others, but it's pretty close to DDU. DDU is the method of Yaring-Gall, which is considered to be state of the art. But on another data set, on ImageNet, we overperform even DDU by large margin. And you see that we are completely almost perfect on ImageNet Air compared to ImageNet. So yeah, it's like reassures that our approach works well. More experiments available in our paper. So yeah, that's all. Thank you for your attention.
Okay, thank you for the presentation. So any questions? Well, I have a question. I see you show the experiment results by ResNet 50 network, right?
Yeah.
I want to know if you try other networks. I mean, whether your results are how to say? I mean, do you try other networks to prove that your method is effective? Just one network may have some errors or something.
Yeah, I can comment on this. In fact, no, we haven't tried, but in the very beginning of the presentation, I told that there are some assumptions or a specific type of networks for which our method works better. And actually, the network should satisfy Beliebschitz assumption. So ResNet plus spectral normalization finally gives us some approximation to this Beliebschitz model. And what we tried, we simply tried ResNet with and without spectral normalization. And we figure out that even without spectral normalization, our method allows us to receive reasonable results, which are still way better than, for example, ensembles on ImageNet. Yeah, but we did not try absolutely different architectures for OOD detection. Nevertheless, we tried other architectures for another experiments like text classification and OOD detection there.
Yeah, okay. So any other questions? Okay, thank you very much.
Thank you.
Then, yeah. So that's all for this session. And next, we will have a 10 minutes tea break. The second session will begin at 20 past 10 at Moscow time and 20 past 15 at Beijing time. Thanks for your attention and see you later.